Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals, right? So in this lecture we'll see how we can find out the value of this integral using the concept of beta gamma functions, right? And moreover in this problem we'll see a number of important results from beta gamma functions which can be utilized in order to get the value of this integral, right? So let us start. So now let us call this integral as I, right? And here the value of the limits, or the lower limit is -1 and the upper limit is 1. So the limits vary from -1 to 1, right? So here we'll make an important substitution, that is we'll take x is t is equal to 1 plus x over 2, right? So here I will make this important substitution. So here we are making this substitution, t is equal to 1 plus x over 2, and let us change the limits accordingly. So when x is -1, then the value of t can be obtained by taking x is equal to -1 in this result. So we have 1 plus -1 over 2, that is 1 minus 1 over 2, that is 0, because 1 minus 1 is 0, right? And similarly when x is 1, then the value of t is obtained by taking x is equal to 1 in this expression. So we have 1 plus 1 over 2, that is 2 over 2, that is equal to 1, right? So now let us rearrange this expression. So we can now write 2t is equal to 1 plus x, or x is equal to 2t minus 1, right? Now let us differentiate x with respect to t. So we have dx over dt is equal to d by dt of 2t minus 1, right? Now see, the derivative of t with respect to t is 1, so we have 2 times 1 minus 0, because the derivative of 1 with respect to t is 0, being a constant. So here we have 2, right? So now we can write dx is equal to 2 dt, right? Okay, so now we can rewrite this integral I as t is equal to 0 to 1, and here we have 2t, because 1 plus x is equal to 2t divided by 1 minus, here we have x can be written as 2t minus 1, right? And here we have the power 1 over 4, and here we have dx is equal to 2 dt, right? Okay, so now we can simplify this expression. So we have 0 to 1, and here we have 2 raised to 1 by 4, then we have t raised to 1 by 4, right? Because see, we are distributing this power 1 over 4 into 2 and t, right? And here we have 1 minus 2t, 1 minus 2t, minus minus becomes plus. So here we have 1, and here we have 1 over 4, and here we have 2 dt, right? So now let us simplify it further. Here we have 2 raised to 1. So 1 over 4 plus 1 is 5 over 4. So we have 2 raised to 5 over 4. And then we have t raised to 1 over 4 dt. And see, here we have 2 minus 2t, right? 2 minus 2t raised to 1 over 4. And taking 2 common, we have 2 raised to 1 over 4, 1 minus t raised to 1 over 4, right? So here we have 2 raised to 1 over 4, and 1 minus t raised to 1 over 4, right? Now see, here we have 2 raised to 5 by 4, 2 raised to 1 by 4, 2 raised to 1 by 4. When we take it to the numerator, we have 2 raised to 5 by 4 minus 1 by 4. That is 2 raised to 5 minus 1 is 4, divided by 4, that is 1. So here we have simply 2, and here we have the limits 0 to 1. Then we have 0 to 1 and t raised to 1 by 4, and here we have 1 minus t raised to 1 by 4. Taking 1 minus t raised to 1 by 4 to the numerator, we have 1 minus t raised to minus 1 over 4, and here we have dt, right? So now we have I is equal to 2. Here we have 0 to 1, and see, here we have t raised to 1 by 4, right? So t raised to 1 by 4 can be written as t raised to 5 by 4 minus 1, right? And here we have 1 minus t raised to minus 1 over 4, right? So t raised 1 minus t raised to minus 1 over 4 can be written as 3 by 4 minus 1, because 3 by 4 minus 1 is minus 1 over 4, right? And t raised to 1 by 4, so 1 by 4 is equal to 5 by 4 minus 1, and here we have dt, right? So why we have expressed this expression like this? Because we know that the beta integral beta mn is given by 0 to 1 x raised to m minus 1 and 1 minus x raised to n minus 1, and here we have dx, right? So if we compare this integral with this one, then the value of m is 5 by 4 and the value of n is equal to 3 by 4, right? And remember, m and n are greater than 0, right? So this is the beta integral, which is also known as Eulerian's integral of first kind, right? So using this integral, in this integral I, we have I is equal to 2 times, here we have beta of mn, m is 5 by 4, n is 3 by 4, right? So we have beta 5 by 4, here we have 3 by 4, right? And now we know an important relation between beta function and the gamma function. Beta mn is equal to gamma of m, gamma of n, divided by gamma of m plus n, right? So taking m is equal to 5 by 4 and n is equal to 3 by 4, beta 5 by 4, 3 by 4 is equal to gamma of 5 by 4. Then we have gamma of 3 by 4, and here we have gamma of 5 by 4 plus 3 by 4, right? Okay, so now we have gamma of 5 by 4. So 5 by 4 can be written as 1 plus, or we can write 1 over 4 plus 1, and here we have gamma of 3 by 4, and here we have gamma of 5 plus 3 is 8, 8 divided by 4 is 2, right? So now here we'll make use of some important other relations, right? See, a gamma of n plus 1 is equal to n times gamma of n, right? This is an important relation where n is greater than 0. So gamma of n plus 1, right? See, here we have gamma of 1 by 4 plus 1. So gamma of 1 by 4 plus 1 is equal to 1 by 4, because n is equal to 1 over 4, and here we have gamma of 1 over 4, right? And we also know that gamma of n plus 1 is equal to n factorial. So gamma of 2 can be written as gamma of 1 plus 1, that is 1 factorial. 1 factorial is 1, right? So now this expression is now equal to beta 5 by 4 and 3 by 4 is equal to gamma of 1 by 4 plus 1 can be written as 1 by 4 gamma of 1 by 4, and here we have gamma of 3 by 4, and here we have gamma of 2 is 1 factorial, that is simply 1, right? So we have 1 over 4 gamma of 1 over 4 and gamma of 3 over 4, right? So now we have written this expression over here, and now see here we have this term, right? And here again we'll make use of a very important result from gamma functions. So we know that gamma of n, gamma of 1 minus n is equal to pi divided by sine n pi, right? So this is an important relation, right? So gamma of n times gamma of 1 minus n is equal to pi over sine n pi, right? And here we have gamma of 1 over 4, gamma of 3 over 4, right? So if we take n is equal to 1 over 4 in this expression, then we get gamma of 1 over 4. Here we are taking n is equal to 1 over 4. Then 1 minus 1 over 4. Right? 1 minus 1 over 4. And here we have pi divided by sine. N is 1 over 4. So this is pi over 4. Right? So gamma of 1 over 4. Gamma of 1 minus 1 over 4 is 3 by 4, right? So here we have gamma of 1 over 4, gamma of 3 over 4, that is equal to pi divided by sine pi by 4. Sine pi by 4 is sine 45 degrees, that is equal to 1 over root 2, right? That is equal to pi times square root of 2, because taking square root of 2 to the numerator. So viewers, now we can write this integral I as 2 times beta of 5 by 4 gamma beta of 5 by 4 comma 3 by 4, that is equal to 1 by 4 times here we have gamma of 1 by 4 gamma of 3 by 4, and gamma of 1 by 4 gamma of 3 by 4 is equal to pi times square root of 2, right? So here we have pi times square root of 2. So this is 2 to the 4. So we have pi root 2 over 2, right? So we can rationalize this term by multiplying the numerator and denominator by square root of 2. So we have here square root of 2 divided by square root of 2, right? So we have square root of 2 times square root of 2 is equal to simply 2. Here we have 2 root 2. 2 and 2 get cancelled. So we are left with pi over square root of 2, right? So viewers, the value of this integral is equal to pi over square root of 2. So this is how we can solve these kind of integrals by making use of all these important results from beta gamma functions. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals, right? So in this lecture we'll solve this important integral using the concept of beta gamma functions, right? So let us start and let us evaluate this integral from 1 to 3 x minus 1 raised to 7 x minus 3 raised to 3, right? And we'll see how we can use the concept of substitution method to reduce this integral into the gamma function, right? So let us first call this integral as I, right? So here I will make an important substitution, and let us substitute t is equal to x minus 1 over 2, right? So here this is an important substitution, right? Okay, now see here x varies from 1 to 3, right? So let us change the limits accordingly. So when x is 1, then the value of t can be obtained by taking x is equal to 1 in this expression. So we have 1 minus 1 over 2, that is 0, because 1 minus 1 is 0, right? And when x is 3, then we have t is equal to 3 minus 1 over 2. This is 2 over 2, that is 1, right? So when x goes from 1 to 3, then t goes from 0 to 1. So now we have t is equal to x minus 1 over 2, right? So we can write 2t is equal to x minus 1. So x can be written as 1 plus 2t, right? Now let us differentiate x with respect to t. So we have dx over dt is equal to the derivative of 1 is 0. So here we have simply 2 times 1, because the derivative of t with respect to t is 1, so we have 2, right? So now we can write dx is equal to 2 dt, right? Okay, so now we can rewrite this integral I in terms of t, right? So we have the limits from 0 to 1, because here t varies from 0 to 1, and for x minus 1, we can write 2t. So here we have 2t raised to 7, and here we have x minus 3. So x can be taken as 1 plus 2t, and here we have minus 3 raised to 3, and for dx we can write 2 dt. Okay, so now we can simplify this integral, and here we have 0 to 1, here we have 2 raised to 7, so distributing the power, here we have t raised to 7, then here we have 2t minus 1 minus 3 is 2, and here we have 3, and this is 2 raised to 1 dt, right? Okay, so we have 0 to 1, 2 raised to 7, t raised to 7, and here 2t minus 2. So when we take 2 common, then we have 2 raised to 3, and here we have t minus 1 raised to 3, and here we have 2 raised to 1 dt, right? So now we have 2 raised to 7, 7 plus 3 is 10, and 10 plus 1 is 11, right? So we can take 2 raised to 11 outside the integral. We have 0 to 1, t raised to 7, and here we have t minus 1 raised to 3, and here we have dt. So now we can write this integral I as 2 raised to 11, then we have 0 to 1, and t raised to 7, and here we have c, we have t minus 1, so we can write 1 minus t raised to 3, and we can take minus 1 raised to 3, and here we have dt, right? So what we have done here, we have written t minus 1 as 1 minus t raised to 3, and taking minus 1 common, because we want to convert this term or this integral into beta integral, right? So that's why we have here minus 1 raised to 3, because taking minus 1 common, right? So expressing t minus 1 as 1 minus t, right? So now we can write this negative 1 raised to 3 is minus 1. So we have minus 1 raised to 11. Then we have 0 to 1, t raised to 7, and 1 minus t raised to 3 dt, right? So let us write this integral as 0 to 1, and here we have t raised to 7. 7 can be written as 8 minus 1, and here we have 1 minus t raised to 4 minus 1 dt, because writing 3 as 4 minus 1 and 7 as 8 minus 1. So now the Euler's integral of first kind can be expressed as beta mn, and we have 0 to 1 x raised to m minus 1 and 1 minus x raised to n minus 1 dx, right? So this is defined as the beta integral, and here we have the variable t in place of x. And if we compare this integral with this one, we have 0 to 1, then x raised to m minus 1, right? So comparing this integral with this one, the value of m is equal to 8 and the value of n is equal to 4, right? So now this integral I is minus 2 raised to 11, and this one is equal to beta mn, and m is 8 and n is 4, right? So now we have beta of 8 comma 4. So now this beta function can be expressed in terms of gamma function. So we have beta mn is equal to gamma of m, then we have gamma of n divided by gamma of m plus n, right? So we have I is equal to minus 2 raised to 11, we have gamma of 8, gamma of 4, and then we have gamma of 8 plus 4, that is 12, right? So to calculate the value of gamma 8, gamma 4 and gamma 12, we'll make use of this result, that is gamma of n plus 1 is equal to n factorial, right, where n is greater than 0, right? So gamma of 8 is gamma of 7 plus 1, that is equal to 7 factorial. Similarly, gamma of 4 is gamma of 3 plus 1, that is 3 factorial here. And then we have gamma of 12, that is equal to gamma of 11 plus 1, that is 11 factorial, right? So now we have here minus 2 raised to 11, and gamma of 8 is 7 factorial, gamma of 4 is 3 factorial divided by gamma of 12, which is 11 factorial, right? So now we have to calculate the value of this expression. So now see, here we have minus 2 raised to 11, 7 factorial, then 3 factorial is 3 times 2 times 1, that is simply 6, and 11 factorial can be written as 11 times 10 times 9 times 8 times 7 factorial, right? So this 7 factorial and this 7 factorial get cancelled, and here we have 2 3s are 6, here we have 2 4s are 8, and then we have 3 1s are 3, 3 3s are 9, right? So now see, we have minus 2 raised to 11 in the numerator, and here we have 11, then 10 can be written as 2 times 5, and here we have 3 times 4. 4 can be written as 2 square, right? So we have minus 2 raised to 11. Here we have 11 times 5 times 3. Here we have 2 raised to 1. 1 plus 2 is 3. So we can take 3 to the numerator. So we have here minus 3, right? So this is minus 2 raised to 8. And here we have 5 3s are 15. 15 times 11 is 165, right? So now the value of this integral I is equal to minus 2 raised to 8 is 256, and in the denominator we have 165, right? So viewers, the value of this integral is equal to minus 256 divided by 165, right? So this is how, by making use of the concept of beta gamma functions, we can evaluate these type of integrals.